Okay, welcome everyone to today's lecture. Thank you for coming. Thank you for watching the video or whatever. So we continue with our story about why the Euler characteristic. So this piece down here is extremely cool. So last time we have seen, well, how to play around with the Euler characteristic of the sphere, right? The only thing we ever did was the Euler characteristic of the sphere to get various, really non-trivial results about platonic solids and polygons in general, like this beast here, or polygon decompositions of soccer balls or anything, or things like that. And it was really not trivial at all. So we played around a bit with those two numbers, P and N, which will reappear today. So recall the numbers P and N. So it was the numbers that were always smaller than 6 for the platonic solids because of this condition we got from the Euler characteristic. There you go. This one here, that 1 over P plus 1 over N has to be bigger than 1 over 2. And if one of them is too small, that just doesn't work out. It's a pretty easy count. And we got a classification of all of them just using the Euler characteristic. We're sure we need to build them, but that's not so hard. The point is that there can't be any other platonic solids, right? If you just would do this yourself, maybe about thinking it for a while, you would come up with those 5 surfaces here. But to show that there are no others is absolutely not trivial. And this was actually a pretty nice proof, just using combinatorics or numerics of the Euler characteristic itself. And very similar was the other argument, like, okay, if you want to build a soccer ball out of octagons and triangles, well, there can only be one solution, which is this kind of surface here that actually even has a name, the octa cube, which was the cube just with cut off corners, essentially. That was pretty good, right? And we would like to continue thinking about the Euler characteristic and getting non-trivial results from the Euler characteristic, because it's just ridiculously amazing and powerful. A very simple formula, and it's actually very, very powerful. So never change a winning team, obviously. So we just push it until we are kind of sure that we have everything, whatever, shown using the Euler characteristic. Okay, so today, a kind of cool topic. I will show you one of the most celebrated theorems in mathematics altogether, the so-called four color theorem. Well, the name already suggests that there are 4 colors involved, I guess. So you will see a few colors. And actually already on the next slide, we will see quite a few colors. So the idea is as follows. So we have, well, this is clearly a map of the countries of the Earth. So which is a polygon decomposition of S2, I guess. Just as usual, so S2 is the surface of the Earth. And the question, which was asked quite early, is how many colors suffice to color the Earth or actually any map? And what do I mean by color suffice? Well, it's pretty simple. So each country gets its own color. So I have what is this, blue as a color, I have red as a color, I have yellowish as a color, and there's green as a color. So each country gets its own color. Like Australia here looks very yellowish, I guess. Let's just be really such it is the polygon decomposition of S2. I will count the oceans as one very huge country, I guess. So it gets its own color, blue. Antarctica, its own color, whatever. Argentina gets its own color, and so on. So everything gets its own color, but there's a rule. Otherwise, it would be boring. Otherwise, you could just color everything blue. The rule is adjacent countries get different colors. Right? So my little ocean here, which I count as a country, remember, every country that is adjacent to the ocean cannot be colored blue because I decided to color my ocean blue. And as you can see, that's actually true on this map. Right? So here's a blue country, and here are some blue countries, but they are all kind of inside of land masses, so they're not neighboring. They don't have any shore. They're not neighboring the ocean. And similarly, if this is red, I can't color Russia red, or China is yellow, so I can't color whatever North Korea yellow, and so on. So I want to give everything a unique color such that none of its neighbors has the same color. Okay, there is a clear upper bound for the number of colors you need, namely just the number of countries. So every country gets its own color. Sure. So we can go with whatever, how many countries, so 200-ish. So we get 200-ish colors here. But there's a really, really amazing theorem that tells you, it's called the four-color theorem, that you never need more than 4 colors. Well, here are my 4 colors, and this is a 4 coloring of the Earth. You never need more than 4 colors, which is absolutely not clear. So I will show you some little animation in a second, and it's not so easy to do yourself. But the theorem says everything gets 4 colors. And this is, so 4 colors suffice. That's what people usually say. And this is one of the most celebrated theorems in mathematics altogether. And 4 colors suffice. There are even post stems celebrating this theorem. So it's extremely amazing. It's very simple. So let me say it again. You have any map, in this case, a map of the Earth. You color countries such that neighboring countries get a different color. And you can always do with 4 colors. Absolutely non-trivial. So let me show you, well, there are even puzzles online, or there's, well, a game, the 4 coloring game on Google Games or something. So this is very, very popular. One of the most celebrated theorems in mathematics, as I said. But it's not so easy to do yourself. So here in this animation, if it actually decides to work, I can color my countries here. And I would need to, well, the game is, of course, to fill. These are countries in a very abstract sense, obviously. And, well, I just need to do this in a way that no 2 different countries get the same color. So, for example, just around this middle, the middle gets some color, so blue. And because all of the rest is kind of arranged around this, such that this red one touches everything else, I at least need 4 colors for this map. I at least need 4. As you can see from this local picture, I show you a nicer local picture in a second. So you can surely convince yourself pretty quickly that you need at least 4 colors. Here's a map that needs 4 colors. I'm not saying that any map needs 4 colors, but there will be some map that needs 4 colors. And here's an example, right? Everything touches everything. So you need at least 4 colors. And the magic of the theorem is that you need never more than 4 colors. Really great. So let me try to fill this in. Maybe it makes sense to make this here, whatever this color is. So it would make sense to make this one the same color and this one the same color. Maybe this one gets green. Green is really bad. Maybe, oh, this was really bad. As you can see, this was already really bad. So let me try again. Let me make this one here. And this one here green. And you would do this one here red, maybe. And we can do this one here in red. We can do this one here in this color, this one here in this color, and we almost won here. Let me just finish it. Maybe this gets green. Maybe this gets purple. And now I messed up again. So maybe this one gets purple. This one gets purple. Oops, purple. Okay, I messed up. I can't do this. It's not so easy. The point is, so you can always do it, and it's really non-trivial. I just messed up the game, right? I lost. So it's pretty non-trivial. Obviously, you could try it yourself. You probably will succeed, and I'm just very bad in those games. Anyway, it's really, really non-trivial. And let me pull up the post stamp again because I like the post stamp a lot. There you go. It's really one of the most famous theorems in mathematics altogether. The proof is, let's say, not very nice, but we will show in this lecture, actually, a weaker version of the theorem, essentially using the Euler characteristic, which is pretty cool. Okay, so here are our 4 colors, and let's now study that more. Like, now that I kind of explained what we want to do, we could try to understand this using the language we already know. So the map is a polygon decomposition of S2, as I said, and so essentially this question involves the same well, combinatorics as we needed for Platonic solids, which is again pretty cool. So it doesn't really look related to Platonic solids, but it's actually highly related to Platonic solids. So maybe we could use the same ideas to attack this question. Okay, so, but we can actually be more general, and we will push that mostly on Monday. It's really, really beautiful. I'll show you some more pictures later. But for now, we just start with any surface, not just S2, could be a torus, a Klein bottle, or whatever you want. And we take this polygon decomposition of the surface, right, the usual one with some vertices, edges, and faces. And we essentially want to think of maps on, for example, a torus. We could think of a torus like being something flat. You all know by now, hopefully, how a torus looks like. And I could draw some kind of countries here on my torus. Note that this country here is this country, would be this country, would be this country, for example. So I could have two countries here on my torus. Right? So there you go, two countries on my torus. And I call them adjacent if they're separated by an edge. So these two countries are adjacent, they're separated by an edge. So I would like to give some different colors, which is really the same as this picture, just on an arbitrary surface. Okay, and I call the minimal possible number that is needed to color something, right? In this coloring, such that adjacent polygons have different colors, exactly as in this picture. I call that the chromatic number of the surface. So chromatic, like colors, and surface, of course, is involved. And precisely the chromatic number of the surface, this is a chromatic number of the polygon decomposition associated to the surface, so of the map, if you want, and the chromatic number will be the maximum of all of them. So the maximal colors needed, you need to color your surface. Right, let me do an example again, maybe again for our world. So you can think of whatever, coloring a map. There was this example here of the map, which looked like this. And this needs, I will have more examples in a second, 4 colors. So if this is P, the polygon decomposition, then CP of the surface would be 4. But I could also have such a polygon decomposition, and CP of the surface would just be 2. So I only need 2 colors to color this one, whatever black and white. And here I need whatever black, blue, maybe red and white. So just the number of colors you need. And then maximize of all of them, because it should be the, well, 4 colors suffice, right? It should be kind of, you want to answer the question, how many colors are actually needed? That's just the chromatic number, and you can do that for any surface. And I will explain what a map is in a second. For now, just go for it. And a map is exactly what you think it is. A mapping, and that's to draw a map on your favorite surface, right? You can draw a map on a torus. Here, for example, you can draw a bit harder to imagine, but you can in principle draw a map on a Klein bottle or whatever. Okay, so that's a chromatic number of the surface. And well, I will tell you in a second what a map is. So for now, we just go for it. And it's really the smallest number of colors we need. So you have a few more examples. In this case, my underlying surface is a disk. So which is just some disk that I've usually like to write as a square, as a rectangle. Here you can see for this map of the disk, 2 colors suffice. So with a fixed P is the polygon decomposition, is the map itself. With a fixed P, I need 2. But of course, this one here, which is a different one, needs 1 more color, so it needs 3. And the one I already showed you needs 1 more color, so it needs 4, for which we conclude that we need at least 4 colors, right? So we get a lower bound for the number of colors. And the point of the 4-color theorem is to say that this is actually an equality, which is highly non-trivial. To find the lower bound, well, again, if you play around with it just for a little bit, it's not so hard. So this example down here is exactly this one, just differently colored, as I've noticed now. But anyway, so to find the lower bound is actually not so hard, but to show that you don't never need any more colors is really complicated. And just think of how complicated a map in principle could be, so that you can color, for example, the Earth with 4 colors. I personally find that very surprising. Like, it's really non-trivial. And as you have seen in my little absolute failure trying to do that game, as soon as you click somehow wrongly in this process, it will go wrong, right? So there will be some solution, but it's not so trivial to find, actually. So very, 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 very surprising theorem, the four-color theorem. I said again, it's so crucial. I know I sound like a broken record, but it's one of the cornerstones of modern mathematics. One of the best theorems. People love it, rightly so. There are post stamps and whatever celebrating that theorem. It's really, really good. And well, obviously, whether we take a disk or a sphere or R2, I hope I convinced you last time that that's the same anyway. And yeah, so for the real world, those are the most interesting ones. But by the main theorem, we now understand all surfaces essentially. So why not do it on an arbitrary surface? There you go. And we will do it on an arbitrary surface. Okay, so one of the best theorems ever, and we will essentially play around with it until mid of next week, maybe we'll see. And let me just tell you what a map is. So for technical reasons, all vertices should have degree 3 because we don't want, well, if you just think of it like one country, you can of course just do the one country like this, but it's a bit boring. So you would have at least some adjacent countries here, and so all vertices are supposed to have degree 3. But that's a harmless assumption. Doesn't really matter, but it will turn out to be useful for calculations. Okay, so all vertices in my polygon decomposition have the same. I have at least 3 vertices. I don't want any polygons that border itself. That's a little bit silly. So what is the coloring problem for those anyway? So yeah, I ignore those. So no borders with itself. In principle, that could happen, of course. Something like this, for example, as a border, and now it's somehow happening on the Möbius strip. So now it has a border with itself. I don't want that. That's just my coloring problem just falls apart for those. So let's not do it. So a map has no country which has a border with itself. You don't want any holes simply because they really don't matter for anything. So let's get rid of holes. We don't want any regions that are completely surrounded. A very simple reason. The coloring problem is just trivial. The region gets a different color and that's it. So we can also remove it from the picture. Doesn't really matter. It doesn't really change anything. And the last assumption, we don't want any stupid internal countries because they don't change anything. So we don't have any stupid internal countries. So these are just assumptions. You might complain now, well, that might be true on a real map. Sure, it might be, but the point is my mathematics gets a bit easier. And if you can do the case without them, then we can do the case with them, because coloring here is essentially trivial for those 2 pictures. Okay, so the last 4 assumptions are just for convenience. Actually, all of them essentially are just for convenience. And if you think about it for a second, then we are essentially still doing the original problem, which was we want to ask about the coloring problem of the planet, of the countries of the planet. This is just, we'll see that improves. It's just easier to do it this way. Say it again, such a situation doesn't really change the complexity of the coloring, so it will be good. Here's the same, here's the same, and this is completely silly, so we also just take it out. Cool. And we want to say something reasonable about those. Again, I pull up my picture. So finding lower bounds is usually very easy, as you can see here, but kind of finding an upper bound, which is what we really want, is hard. And we can actually do this with our Euler characteristic. So the Euler characteristic, what a beautiful tool, gives us a way to understand colorings of maps, which I personally find very surprising. It looks completely unrelated. At least I think it looks completely unrelated, but it's not. It's kind of pretty cool. So again, keyword is Euler characteristic. We will use our good old friend, the Euler characteristic. All right, so we have a map of a surface. And what we do, which is very useful for calculations, is we set the average vertex degree. By definition, this is just this number. Why is this the average vertex degree? Remember our formula that the degree of vertices just sum up to twice the number of edges. So the average vertex formula is somehow just if everything here has its own degree and you just divide by v. So the average degree of a vertex will be exactly this number here. 2 times the number of edges divided by the number of vertices. Average vertex degree. For a very similar reason, I mean, exactly the same reason actually, we have the average face degree. Remember that we had the face formula, degree of a face, sum of all of them is twice the number of edges. So again, the average degree of a face is this formula. So delta V, average degree of vertices, delta F, the average degree of a face. Okay, and as you can see here, by definition, twice the number of edges is just as it should be the average degree times the number of vertices, respectively. So this is this one here, respectively, the average degree of a face times the number of faces. That's essentially, if you think about it for a second, that's essentially how you would define an average degree yourself, right? It should be kind of, if you take it to the number of times it appears, it should spit out, in this case, 2e. So have we seen that before? Let's think about it for a second. Well, I have some comments before, and then we will think about it for a second. So certainly the average vertex degree is at least 3 because of this assumption. But anyway, so the second assumption, no region has a border with itself, implies that the average degree of a face is one smaller than the number of faces. So that should be true, and it actually is. It follows from the other assumption. And here comes my remark, but we'll go back in a second. For platonic solids, actually are 2 numbers that played the important role in the argument. We'll go back in a second, are exactly the average vertex degree and the average face degree. For a platonic solid, a bit boring because they're exactly the face degree instead of the vertex degrees. But that was the reason why they played such an important role in the argument. So if you remember, going back quite a bit to the platonic solids, somewhere here, so those guys are the average face degree and the average vertex degree, and they turned up in the most important formula we were able to kind of derive from Euler characteristic in this case. So 1 over the average vertex degree plus 1 over the average face degree is bigger than 1 over 2. Right? That was kind of the conclusion we had here. So maybe if we know that, here again, the formula should look very familiar now. That's exactly how the average vertex degree and average face degree were defined. If you just swap n to this side and just p to this side, and so just swap those two, yeah, by algebra autopilot, this is exactly how they were defined. And this played the crucial relation here. So maybe, that was the main idea now, maybe we can use those numeric invariants of our polygon decomposition to say something non-trivial by playing some Euler characteristic magic like we did in this example. Okay, let's go back to what we did, the coloring problem for maps. Here was our assumption, and here we go, the average degree formulas. Right, so this is really just generalizing what we have already seen anyway. I hope that makes some sense. So maybe we should be actually able to play around with those a little bit and get some non-trivial results about, well, the coloring problem. Eventually, we hope to show this theorem here for color suffice, but we will see that we don't quite show that. It's sadly not as easy. Kind of the Euler characteristic fails by 1, if you want. We'll see what that means. So it's almost perfect. So let's discuss a lemma here. The lemma looks quite similar to what we have seen already. There's a 1 over 2, there's some minus and whatever. So let me just say, if you have a map of a closed surface, there's the Euler characteristic of the closed surface, and then the average face degree is given by this formula. Okay, that's a lemma, that's just some formula, which we will use in a second. So let me show you. It's really just playing around with the numbers. So let me show you how that actually works. Not so important to really remember the formula. It will be important to get a better formula, or a formula that we really want. I claim that is a simple calculation with the Euler characteristic. It is really not hard. I mean, whatever simple means, but it's really not that hard. So as usual, you just write down the Euler characteristic. Just the formula should stay in your head, I guess. It's really important. Vertices, edges, faces, alternatingly summed up. And, well, we want to say something about the number of faces, so let's keep f, and let's replace v here by this expression, and e here by this expression. So why does it work? Well, let's go back to this expression here. So if you rewrite this, you can replace e, right? So you can replace e by, for example, delta v times v over 2. And that's what I did here. I just replaced it by delta v times v over 2. Actually, I did it the other way around. I can also replace it by, let me redo this. I wanted the faces, so obviously I can also use this one here, and I get delta f divided by 2, which is what I did here. Delta f number of f divided by 2, and similarly you can now replace this one. You can relate those two. So if you relate those two, then the number of vertices is equal to delta f number of f divided by delta v. So again, I hopefully did exactly this replacement here, and indeed, luckily I really did that. And you get now an expression that Euler characteristic is some multiple of f, right? And you just arrange it differently, and algebra autopilot gives you, it's really just arranging the equation slightly differently by factoring out f and then dividing by f, and you get this equation here on the other side, right? So it's just really just this remains here, this and this remains, and then the 1 for f. Okay, and well, now you can rewrite and just solve for delta f. That's all we do here. If you solve for delta f, you get exactly this expression. Okay, it was, I claim it was not so bad. It's really not so bad. It's just replacing everything by what we already know should be true, and then just do some algebra autopilot. And you get this formula, which a priori, I said again, is not important by itself, but it will be useful to get some interesting result. Right, and this is again just a calculation with the Euler characteristic. We will see 1,012,000 of those, and we have already seen 1,012,000 of those. Cool. And the corollary, which is really the main point of this whole slide, is that this number is actually smaller than this number here. 6 times 1 minus delta of s over f. The average number of the average phase degree is smaller or equal than 6 times, so this guy here, and we just say the following. We just say that this one here is at most 6. So can we see that? Well, by assumption, we have this equality, and if this one is bigger than 3, then the smallest one that's possible here is, of course, 4/3. So it's 1 over 6, and this is where the 6 comes from. So this is at least 1 over 6. It's at least 6, so it's at least bigger. So this is the lower bound that upper bound that we get here. So we get an upper bound by just using some Euler characteristic calculation. Okay, and yeah, of course, just fitting it together gives us what we wanted. Okay, so why is that interesting? Why do we want the delta f is smaller or equal than 6 times 1 minus Euler characteristic over f? Well, let me show you the final statement of today, actually. And then I will comment a little bit on what we are going to do next week and repeat a little bit what we have seen today. Why is it good? So this one is just some technical playing with symbols, if you want. But this one is cool because for a map of S2 or P3, then the average phase degree is at most 6. which is quite some step towards what we want to show. We can't do that today anymore. The proof will take a while, but we do that on Monday. But for now, this is just a statement. We have a map on either of those two. Of course, the most interesting one is this one. I mean, the map on the projective plane, I guess, is complicated by default. But then we have that the average phase degree is at most 6. It's at most 6. Not even at most. It's strictly lower than 6. How do we do that? Well, we just feed it in, and we know what the order characteristic of those two surfaces are. Note that at one point we had this assumption on a closed surface. So these are the only ones where we could really do this trick. So this one, the next closed surface, if you remember, was the torus, which had order characteristic 0. So if this is 0, we don't get strictly smaller than 6. So we at least want to subtract something here. So we need those two surfaces. That's why they come in. But then it's kind of clear. So you subtract something that is not 0 from 6. So there you go. And, well, you get the result. Right? So you subtract 1 minus 2, or for example, 2 over f, which is certain, as we multiply this with 6, which is certainly smaller than 1. So you get that this is smaller than 6 in this case. Similarly for the projective plane. And this is a special case. So as I said, we generalized what we know about platonic solids because, well, platonic solids was this case, and we wanted that one of them, let's go back. Well, this probably takes probably too long. Let's go back faster. There you go. Somewhere here, we wanted that the average degrees are bounded by 6. And now we get this result in complete generality for maps, even on the projective plane, but we're really interested in the surface. So here, n is always smaller than 6. And that's exactly what we are seeing down here, somewhere. Here we go, in more generality. So this was a generalization of a statement that we had for platonic solids. And of course, because it's a generalization, actually we proved it. So we found a better way, a more general way to prove exactly the same statement, but now just for all maps on either of those two. Note again that the torus fails, so it doesn't work for the torus, doesn't work for the Klein bottle, and so on. But it works for the first two with the positive order characteristic. Okay, and if the average phase degree is less than 6, then there must be a phase, obviously, with degree smaller or equal to 5. If the average is lower than 6, there need to be some phase with degree lower or equal to 5. And this will help us, this will be the key to, on Monday, prove the 5-color theorem, which is not quite what we really want. Obviously, we want 4 colors suffice. But turns out that the 5-color theorem is provable in a lecture like this. It's not so hard. It's actually probably the most beautiful proof that I'm going to give in this lecture. It's pretty cool. Not so hard. Uses the order characteristic, in particular what we just did. But we can't quite get the 4-color theorem. And even up to this date, there is no really nice known proof of the 4-color theorem. So it's not like I'm certainly lazy, but it's not like I'm lazy and I'm just skipping the proof of the 4-color theorem. It's really that there is no nice proof. So I can't present you anything that is really easy to digest. It's actually worse. So all proofs of the 4-color theorem use computer assistance. So that essentially they work as follows. So you reduce the 4-color theorem to a huge number of cases you need to check by hand, and the number of cases you need to check by hand is just too huge to check it by hand. So you feed the problem in the machine checks it for you, and that's it. That's not a very nice proof. That's like, okay, we can't really do it, let the machine do it. Fine. But anyway, we know, say it again, it's true. So this post stem is not lying, 4 colors suffice, but we only get a proof for 5 colors. Turns out, very, very beautiful, that in general, we will get an analog statement for all surfaces, like the torus, the Klein bottle, whatever. You know how the surfaces look like by now. And turns out that in this case, we can prove the sharp upper bound. Let me say this again. Here for the sphere, we want that this funny number, which is what we really study right now, this was just doing some nonsense around, the chromatic number of the sphere. So what we get from the 5-color theorem is that the chromatic number of the sphere is at most 5. That's what we will show. And we will see that we already saw that it is at least 4. Remember that we had this picture, so it's at least 4. But we still can't decide whether it's 4 or 5. Turns out to be 4, but we can't really prove that. We only get this bound. And for any other surface, for all other surfaces, we will actually do that. For all other surfaces, we will be able to nail down this one precisely. There will be a precise number determining this coloring, which is a really non-trivial statement. So somehow, in this regards, when it comes to coloring of maps, it turns out that the sphere is the most complicated one, and even coloring projective planes is easier than coloring spheres. So maybe we are just unlucky, and it would have been much better if the Earth would be a projective plane. Who knows? Because at least coloring problems of countries would be easier. Just kidding here, of course. The point is, and we'll see that next week, really beautiful theorem, that in this regard, the sphere is the most complicated object. Just very, very strange, very, very surprising. Anyway, so let me show you one more. So, as I said, we don't show it, but the colors needed for the coloring problem of the sphere is 4, and the coloring of the torus, for example, is actually 7. And we will show that. So 7, how does 7 work? So what I'm saying is, if you draw a map on a torus, there will be a map that needs at least 7 colors, and I can show you one. I can actually show you 2 pictures. They're essentially the same. So here's our good old friend, the torus, right? I hope we understand the torus by now. Note that 6 is coming out here, so it's re-entering here, because that's how the torus works. 4 comes out here, so it's re-entering here, and so on. 2 goes up to the top, so it's re-entering from the bottom. And as you can see, let's say 5 in the middle touches everything else, and actually everything touches everything. So you need 7 colors for this. So what do we have here? What is it? Yellow, there's a green color, there's a light blue color, there's a purple color, there's a dark purple color, or maybe light blue, or some bluish. There's a gray color, and there's a orange type color. So you really need 7 colors on a torus. And why is that? Because of the geometry of the torus itself. So this question here, show you another picture in a second, is actually related to the topology, the intrinsic properties of the surface, which is pretty cool, because that's what we want. So intrinsically, the sphere is different than the torus, and you can see that because maps on the torus need more colors than maps on the sphere. And I will write down, as I said, a precise statement what these numbers are for all surfaces, which is a really cool result eventually. And maybe the second best result we'll show in this lecture. So let me pull up one more picture, which is again the torus. So again, the same picture. So green exits here, enters here. So whatever, this light blue here and here. So it's really the torus. And this was the map I showed you at the very beginning. So it's a little bit easier to see in the other picture that everything touches everything, because it's essentially a hexagon tiling of the torus, right? Here, everything here is a hexagon. Hexagon has 6 neighbors. So there you go, it goes 6 around, but everything now touches everything. So this one also touches the yellow one because it goes around. This one touches the yellow one, and so on. So everything touches everything. And you need 7 colors, and 7 is exactly the arrangement of the hexagon around a center. Okay, and we will show something similar and related for, I show you some more pictures for the other, well, here's another one for the other surfaces. So here's the coloring, a map on the Klein bottle, which needs 6 colors, I guess. Let's see. The one in the middle is adjacent, so this is yellow, is adjacent to purple. Purple goes all the way around. It's adjacent to blue. Blue also goes all the way around. There's a red one that goes around like this. there's a light blue one and there's a green one. So green, light blue, red, dark blue, purple, and yellow are 6 colors, and everything again touches everything because you can use the geometry, the topology of the Klein bottle to make the ones from the top touch the ones from the bottom. And will turn out that the chromatic number of the, we will write down a formula for all chromatic numbers of surfaces, which is the goal for next week. Okay, so that was what I wanted to say for today. Let me just repeat what we have seen. And I already spoiled where we will go. We will essentially see the famous 4-color theorem now for all surfaces, which is absolutely great, which is absolutely a great result. So here the 4-color theorem. And very natural question. Coloring of maps such that adjacent countries get different colors. And you get the surprising answer, as you can see here, that 4 colors actually suffice, which is really, really a non-trivial result. And we'll see that for every surface. So a similar formula for every surface, because by now, I hope you remember that one of my main theorems here was the classification of surfaces. So we understand surfaces very well. So what you should do now is to study kind of notions related to surfaces. In this case, we study maps on surfaces. Before we studied polygon decompositions of surfaces in a certain specific way, like platonic solids, and now we study polygon decompositions of surfaces in the sense of coloring them, in the sense of maps. And what I'm really up for is this number here, the chromatic number of a surface, and we'll compute those numbers in on Monday, actually. And remember here, it's usually very easy to find the lower bound. So let me show you all lower bounds again. So here's a lower bound. Let's go to the end. So here, 7 was my lower bound for the torus. I have another picture for the torus. Again, 7 colors on the torus really uses the geometry of the torus. I had the Klein bottle, 6 colors on the Klein bottle, uses the geometry of the Klein bottle. And of course, we also had, where are we? Here we are, the 4-color theorem, 4 colors on a disk. Right? So say it again, this number, which will be a really beautiful formula in terms of the Euler characteristic, just captures kind of combinatorially the properties of the surface. Anyway, that's it for today. Hope to see you.